Hello, everyone. Am I audible? Good. Thanks for the introduction. Hello, everyone. I am Ashutosh Dhekne. I'm here to talk about LiquID, a wireless liquid identifier. This work has been done with my collaborators, Mahant, Yujuan, Haitham, and Romit. We are all from the University of Illinois at Urbana-Champaign. The goal of this work is to identify liquids using wireless signals. We would like to transmit a wireless signal through an unknown liquid, observe the properties of the signals coming out of the liquid, and say that it is actually Pepsi. Not only that, we would want to obtain such precision that we will be able to even distinguish between Pepsi and Coke. And using the same approach, we want to distinguish also not just between a few carbonated drinks, but also apple juice and orange juice, whole milk and skimmed milk, olive oil, peanut oil, various alcohols, even distilled water and mineral water. A lots of work has gone into trying to identify liquids, trying to look at their properties and so on. However, there are three key limitations to these existing techniques. Most of them require you to dip a probe inside the liquid. Many of them actually perform chemical analysis, which essentially is heating, treating, or beating the sample. And many of them are also extremely expensive and very bulky. Instead, we want to enable liquid identification without touching the liquid by simply passing wireless signals through the liquid and in an inexpensive way, probably by building a $100 equipment, for example. As a result, this will open up a lot of applications in various avenues. One application is in airport security. Today, we are not allowed to carry more than 3 ounces of liquid in our carry-on bags. If we enable a simple, non-invasive way to identify liquids, it may be very easy to carry a bottle of water or carbonated drinks in the airplane. In many places around the world, contaminated tap water is being sold in the disguise of mineral water. If we could create a device that quickly identifies one from the other, it will be useful in countries such as in India, for example. Maybe in the future, we could create a smart cup that identifies the liquid a user is consuming and then records the calorie intake without any inputs from the user. Now that we know what we want to achieve, the question is how do we get there? And for this, we want to start to understand how signals behave inside a liquid. When we shine a wireless signal onto a liquid, there are two key properties that play a role. First, the signal gets absorbed inside the liquid. And second, it bends towards the normal. The signal bending is of course due to the liquid's refractive index. And the reduction in signal strength is due to its attenuation factor. These two, the refractive index and attenuation factor, form a tuple, which is quite unique for every liquid. So now we have to measure refractive index and attenuation factor. Let us look at the easier thing first. If we shine a signal and measure the amplitude of the received signal, we will be able to estimate the attenuation factor pretty easily. So that this is out of the way, let us now zoom into the refractive index. For most of us, refractive index is essentially the ratio of the incident angle to the refracted angle. In this example, sine alpha by sine beta. As signal passes into different materials, the signal bends, giving us these two angles. These angles can be measured very well in the optical realm when we have laser-like beams. However, with wireless signals, where the beams cannot be that narrow, it is actually very challenging. So much so that even in physics textbooks, they say that this is of great complexity. But there is another interpretation of refractive index, which relates to the velocity of signals. If you shine a signal perpendicular to the liquid surface, then the signal will not bend, but it will definitely still slow down. Refractive index is also defined as C by V. Now this gives us the opportunity. In other words, if somehow we can measure the amount of time it takes for signals being transmitted from the left-hand side to go to the right-hand side, we might be able to get the refractive index. We will use this approach of measuring Ri in this work. Now that brings us to the question, how do we measure this slowdown accurately? The answer comes from wireless localization literature. In localization and ranging, people are interested in determining the distance between the transmitter and the receiver. And the way to get to this distance is by measuring the amount of time it takes for wireless signals to travel from the transmitter to the receiver. We call this time of flight, or TOF. Now, suppose we place a column of liquid between the transmitter and the receiver. Then the time of flight will be larger, right? Why? Because the signals will slow down inside the liquid. And now because of that, if we do the math properly, then we get the difference between the time of flight with liquid and that without the liquid is essentially equal to d by v minus d by c, where d is the width of the liquid column, c is the velocity of light in vacuum, and v is the velocity of wireless signals inside that liquid. Since v is the only unknown, if we measure the TOFs properly, we should be able to get to the refractive index. So now it boils down to being able to accurately measure the time of flights. What are the resources available to us to measure this delta time, or even individually the time of flight with the liquid and without the liquid? Today, we have ultra-wideband radios. They have 1 gigahertz of bandwidth. They are inexpensive enough that they would be useful in our applications. And 1 gigahertz of bandwidth results in a time granularity of around 1 nanosecond. So is this good enough? The difference in slowdown between Pepsi and Coke, for example, is of the order of few picoseconds. So with a nanosecond level of granularity that we are going to get with commercial off-the-shelf UWB platforms, there is no way we can distinguish between the two. In fact, if we tried, we would get the answer as soybean oil, for example, completely different. This measurement of TOF at picosecond granularity is the key challenge in our work. To solve this problem, our contributions are twofold. One is architectural, and one is algorithmic. Let's look at the architectural change first. We introduce a wire between the two devices that allows us to move from absolute measurements to relative measurements. This becomes crucial in being able to overcome clock synchronization issues. This wired reference path also allows us to cancel many hardware variabilities. Further, we jointly solve the phase and the received signal, the phase of the received signal and the time of flight to bring down the nanosecond granularity to a few picoseconds. Let me now elaborate a little bit about how we achieve this and how exactly connecting a wire helps us. For that, we should take a look at the channel impulse response. What is the channel impulse response? When wireless signals are sent by a transmitter, they arrive at a receiver over multiple paths. Now, if we transmitted just an impulse, then a time domain representation, shown here, of all the echoes arriving at the receiver would be called the channel impulse response. Of course, since we cannot just send an impulse, we have to send slightly bigger pulses. The channel impulse response received at the receiver would actually be a little bit more spread out. In most localization use cases, the only first peak is really used, and the other peaks are left unused. And that is because the first peak already gives us the direct path between the transmitter and the receiver. By connecting the wire, however, we introduce a new peak in the channel impulse response. The first peak corresponds to the shorted wired path, and the second corresponds to the signal received through the air path. Now, if we introduce a liquid column between the two antennas and send another wireless signal, the signal will slow down, and this slowdown is observable in the channel impulse response. T liquid has actually shifted to the right of T air. Nothing has influenced the wired path, so that remains intact. Now what we really want is the difference between the blue and the green line on the right. But these lines correspond to two different wireless packets. As a result, they are not directly measurable. So how do we measure them? Notice that we could actually subtract the time of the blue path from the time of the red path, and in a separate packet, subtract the time of the green path from that of the red path. A difference between these two will basically give us the time delay that the liquid has caused. And since both of these quantities are measurable, we can do that. So this difference between the green and blue peaks indicates the slowdown caused by the liquid. However, a very small error in this peak detection can cause a large error in the actual time of flight obtained. So now what do we do? Well, there is some more information left in the CIR which we have not yet used. Every point in the channel impulse response also has a corresponding phase. The phase tells us how much fraction of the wavelength a signal has traveled. Of course, it could have traveled more than a wavelength. That the phase cannot tell, but we'll worry about that a little later. For now, observe that the phase information is directly obtained via sampling at the receiver even before the filters are applied. As a result, the phase under a channel impulse response peak remains fairly stable over a larger period of time. We can therefore compare phases to improve precision. Now, in a similar spirit that we used for the time of flight, we can also start to compare the phase that we receive at the without the liquid and with the liquid. At this point, it is tempting to start denoting this phase as a measure of the slowdown. However, phase wraps. So we cannot directly associate that with the actual slowdown. Now, what that leads us to is that we cannot completely eliminate the use of the time of flight information that we derived before. We jointly solve the phase and the time of flight such that we can arrive at a much better estimate of how much time it has actually taken. So if the time of flight is off by a little bit, we can actually use the correct phase and readjust the time of flight to get a better estimate. This essentially is enabling us to bring down our time granularity from being in nanoseconds to being in picoseconds. Now, with this refined estimate of time of flight, we are able to obtain refractive index of the liquid. We are still left with the attenuation factor. We just told you at a high level how it is done. But luckily, the same reference wire that we used to better the TOF estimates is also going to help us with the attenuation factor. It is obtained through the ratio of the wireless peak with and without the liquid. Now, the alignment at the wired peak is crucial here because that eliminates amplifier gain problems, automatic gain control differences, and hardware noise at the received signals. Remember, these are two different wireless packets, so they would have all of these problems without the reference wire to align at. So now we have both the refractive index and attenuation. This is the unique tuple that we were after, and this is the one that will enable us to identify liquids. Let us take a look at the experimental setup we had. In our evaluation, we used two Decawave UWB boards. They were running at 4 gigahertz frequency and had 1 gigahertz of bandwidth each. The CIR data that we talked about was obtained from the receiver, and finally, this gave us the refractive index and the attenuation factor. We did this for 33 different liquids, which span a large part of the refractive index space. So this includes water, water solubles, oil, various oils, alcohols, and so on. We used a vector network analyzer as a baseline or as a ground truth mechanism. A dielectric probe is dipped into the liquid, and it gives us actually the complex permittivity of the liquid. The refractive index and attenuation factor together is sufficient to actually derive the complex permittivity. Now, to make the comparison right, we actually converted our refractive index and attenuation factor to complex permittivity. And the median error in the real part of permittivity is around 9%, whereas that in the imaginary part is around 12%. This compares well with the VNA's published error margin of 5%. So that is a $134,000 setup. Ours costs in manufacturing could cost around less than $100. Most of the liquids could be easily identified during repeated tests with the liquid setup. During each test, the permittivity was calculated and the closest matching liquid was returned as a result. Some of the problems we noticed while actually just doing the experiments pertain to refrigerated drinks, because as the temperature changes, the permittivity shifts as well as some of the drinks which actually age, things like milk, for example. It was very difficult to do an exact analysis. Of course, there are limitations to what we can achieve. We cannot tell components of a mixture, so we can finally only give you a refractive index and attenuation factor and a permittivity, but we cannot tell what it is exactly composed of in minute details. Also, containers of any size and shape will create problems, and that remains an open problem for us to look at. We set out to identify liquids by shining wireless signals through them. We had the option of using machine learning where we could have looked at various features of the outcoming signals and could have run classifiers. However, we chose to not use machine learning and rather model the actual signal behavior using properties of physics, and ultimately arrived at two fundamental properties of refractive index and attenuation factor. This is the reason that we believe our technique is generalizable such that even if we have only used 33 liquids in this paper, we could actually tell these two properties of any unknown liquid. I wish to thank my collaborators and all my lab mates for putting up with all the liquidy mess that I created in the lab. And thanks for listening, and I'll take questions now.